Hey guys, this is AI Yinsh group project presentation. Next, we are going to introduce our AI agents. We have designed 4 agents, which are minimax tree with alpha beta pawning, SASA, approximate Q-learning, and multi-color tree search. Agent 1 is minimax tree with alpha beta pawning, and it is our baseline algorithm. Alpha beta pawning reduces the number of nodes evaluated by the minimax algorithm in its search tree by using a pawning algorithm. This algorithm performs well if the heuristic is good, and it is easy to implement. The heuristic we designed for this algorithm is according to the reward score provided in the Yinsh model. Our agent's score will have more weights than the opponent's agent's score, so that we can keep telling our agent that he is likely to win. This heuristic is not unmissable, but go aware. This algorithm has some disadvantages. It is very slow, although we cut many nodes, and it takes too many memories.
The agent 2 is the Sasha algorithms. In the name means state, action, reward, state actions. And that is exactly why we think this algorithm can be applied in this project, because in the most of the time we also focus on the state and actions in this game. And in the implementations, we need to make this algorithm update the Q value after each action is actually taken. And with that, we need to design the unique reward functions for the updating based on the game rules. Ideally, such an algorithm will have a good performance if it has a suit Q table to the game. But in the real process, we found there are some problems, like it is not easy to determine a good Q table, or like the Q table can be very large in such competitive games. So here are some future improvements can be done, like using pre-training or pre-learning, or manually set a Q table for the agent first, expand the updating range, or make the iteration rate to decrease gradually to make the learning is convergent.
Our next technique is multi-color tree search. In the algorithm, when we select a node, we need to check it is fully expanded or not, but it's unnecessary in this project because we've done an experiment. Our algorithm can check 18 nodes in average in 1 second. However, for example, if we choose child node 1 from root node, we also need to check 18 nodes to determine whether it is fully expanded or not, which means our algorithm will stop at the selection part, which is unacceptable for multi-color tree search because it will just choose a random action. Instead, we build a dictionary to check all the nodes we have visited. For example, we choose child node 1, it is in the dictionary. Then we go to the next layer. We repeat this until we find child node 3, which is not in the dictionary. Now let's see a demo of my algorithm. We can see our algorithm can find a way to reach the goal. We also implement an opponent strategies in the simulation part. We record the path that the opponent can reach a goal, and in the next simulation, we will try to stop these actions. Our algorithm performs good if it can find a reward, but extremely bad when the dip is not enough for the algorithm to find a goal. It is just like random choose algorithm. Okay, next.
Now it's time to introduce the 4th agent, which is approximate Q-learning. Its performance depends on the feature selection. We have 5 features in total. The 4th feature is pre-calculated, and it assigned a heuristic value for every possible 5 long states of the game ball. Since the SASA used a Q table which occupied too many resources from the computer, this algorithm is different. It changes the Q table to features and weights, so that it is extremely fast and efficient. However, the feature selection needs the designer to have deep understanding of the game. Therefore, we only have 5 features. A new strategy of selecting 5 rings shows in these 2 pictures. We change to select a ring's position which is closest to the center of the ball and opponent's rings. This strategy helps the agent to be more likely to block opponent's counters later. Overall, the approximate Q-learning has the best performance among the 4 algorithms. We used it for the final tournament, and we rank around 20th place. That's all. Thanks for your attention.